All right, hi AS Chem. This is a video on 11.2 acids and bases. Almost done of the year, second to last lesson. So this is a quick little overview of the basics of what you need to know about acids and bases. There's three topics that you need to know here. For one, we're going to go over the Arrhenius definition of an acid and a base. Number two, we're going to go over the Bronsted-Lowry definition of an acid and a base. And then number three, we're going to talk about pH, OH, and do some calculations with that. And so let's dive in with the Arrhenius definition of an acid and a base. In the 1800s, this guy named Arrhenius, a Danish chemist, classified or created definitions for these two classes of compounds that we had. We basically had these things which destroyed stuff, which for the acid it tasted sour, for the base it tasted bitter. One of them turned litmus paper red, one of them turned litmus paper blue. And so we had these two things and we needed to give a definition for them. And what Arrhenius noticed is that basically the things that had that were sour, that turned litmus paper red, that destroyed things, these, all of them, their chemical compound had an H in it. Whereas the things that were bitter, that also destroyed things, that turned litmus paper blue, all of them had an OH in them. And so Arrhenius created this definition that basically an acid is anything with an H, and a base is anything with an OH. And this was a pretty good example. It gave us two kind of boxes that we could put stuff into, and it got us started. And so we can use that definition here to classify these six compounds as an acid or a base. And so we look at HCl, and we see that it has an H. And so based on this definition, we know that it's an acid. We take a look at number two, we see it has an OH, and so based on that definition, based on the definition of up here, we know that this is a base. Here, again, we can see that there's an H, and so this is an acid. Here, there's an H, and so this is an acid. Here again, H, and so acid. And then here we have an OH, and so this is a base. All right, and so pretty simple definition. Now, one thing, though, that you may have noticed is that here, H2O is an acid, here, HOH is a base. But these are actually the same thing, right? H2O is HOH, right? And so, right, to H2O, and so, yeah, you know, I'm just kind of writing it in a different way. And so, what we can see here is that there are things that have H's and OH's, and we call these things amphoteric substances. These are substances which can be an acid or a base. Now, basically, the problem was Arrhenius' definition didn't account for amphoteric things. These things were either acid or a base, right? They couldn't be both. And so this is what led us, actually, this idea of amphotericity and other complexities, is what led Bronsted and Lowry to create a better definition that encompassed more things. And so the Bronsted-Lowry definition was things could actually be an acid or a base. It depends on the situation that they're in and what they're doing in that situation. An acid is something in a chemical reaction that is giving up protons, H pluses, whereas a base is something that is accepting protons, H pluses, in that reaction. In this example, what we can see is that it depends on what that substance is doing in that reaction. So for this definition, it depends on what the substance is doing. If it's giving up H pluses, it's an acid. If it's accepting H pluses, it's a base, and it can act as either one, depending on what it's doing. And also, in this situation, right, if someone is accepting H pluses, it must have been because someone else was donating them. If you're donating, it must be because someone else is accepting, right? And so they act as pairs. You have acid-base pairs in a reaction. And so that's why here, with the examples, I have to do an entire reaction, because that's what the definition requires. And so here, we take a look at this example, and let me walk you through kind of how I read through it, kind of my logic whenever I do these. And sorry, let me make sure this is straight. Whenever I'm doing these, what I do is I take a look and I say, okay, well, I have HCl here, and what happens is it combines with NH3, and I make NH4 and Cl minus. And so I see to myself, I'm like, okay, NH3 became NH4. That must have been because it got the H from HCl. And so here, what we're seeing is NH3 is a H plus acceptor, right? It's accepting H's, and so it must be a base. Whereas HCl, it's giving up its H to NH3, right? to become Cl minus, and so it must be donating its H plus, so it's an acid. Right? And so if you read it through like that, what you'll see is that you'll be able to apply these definitions. And so let's take a look here, right? We go F minus and H2O, we make HF, and so F is gaining here and is gaining an H, and it's getting it from H2O, which becomes OH minus. And so what we see here is that the H is being donated here, so this is the acid, and this guy is the base. Very nice. And then here we have NH4, it's becoming NH3, so it's the one who's giving up its H, and so it must be the acid. And I'm sorry, it's not straight at all. All right, okay. And so Cl here is gaining the proton, and so it must be the base, right? And so that's how you classify things as acid or a base based on the Bronsted-Lowry definition. Now, last thing to notice here, though, is that number 3 is actually the opposite of number 1, right? Did you notice that? Right here, HCl and NH3 make NH4 and Cl minus, and here, I just took these guys and I was like, okay, well, what if we go in reverse? Right, remember, we learned about equilibrium reactions, and we learned that a lot of reactions are indeed they can be reversed. And so, yeah, acid-base reactions are also very reversible. And so, you know, what I actually should have done is I should have drawn out the arrows like this. And so if we draw it out like that, right, what we see is that actually, if there's an opposite reaction on the other side, we can also actually classify these guys. And so what we see here is that this is the acid, and this is the base on the other side, right? And so if we're going this way, NH4 is actually the one giving up the H plus to Cl minus, and so it's acting as acid. Now here's an interesting thing. NH3 was a base, then when it became NH4, it became the acid. HCl was the acid, then it gave up its H, it became the base. Acids become bases, bases become acids. We actually call these conjugate pairs, and so this is not just the acid, it's the conjugate acid. This is not just the base, it's the conjugate base. You have learned about base or conjugates in math, where you learned about like when you were doing imaginary numbers, a plus bi, its conjugate base its conjugate is a minus bi, right? And so basically conjugate is like opposite pair. And so what we see here is the opposite pair of the acid is its conjugate base. HCl, when it loses H plus, it becomes the conjugate base of Cl minus. And so all you have to do, simply put, is to say, okay, if this was the base, on the other side, it's going to be the conjugate acid. If this was the acid, on the other side, it's going to become the conjugate base. Here, this was the acid, it's going to become the conjugate base. On the other side, this was the base, it's going to become the conjugate acid. And so it's that simple. So that's the Bronsted-Lowry definition. Last thing I want to go over with you guys is pH and pOH. And so pH is a measure of the acidity of a substance. You probably have learned about it at least a little bit in middle school, if not in biology, where you use litmus paper, right? And so pH measures acidity, with a 1 being very acidic and 14 being not acidic at all. And so it's on a 1 to 14 scale, kind of the same way that GPA is on a 0 to 4 scale, right? 0 is bad and 4 is great, you know, perfect. Though, you know, other GPAs are also great. But it's a 0 to 4 scale. Here it's a 1 to 14 scale, with 1 being the lowest. Actually, I guess it could go 0 to 14, to be honest. So maybe I should change this to 0. Though, not very theoretically possible. But yeah, you could. Yeah, actually, it is theoretically possible. But depends on substance. Anyways, tangent. 0, very acidic. 14, not acidic at all. 0, very basic, versus 14, not basic at all. I'm sorry. 14, not acidic at all. Sorry, I haven't gotten pOH yet. And so that's pH. pOH is a measure of the basicity of a substance. And so in the same way that we have a measure of acidity, pOH measures basicity, with 0 being very basic and 14 being not basic at all. Well, that's the second bell, so that I have to let in my third period. So I am going to pause this video, and then I'll upload a second video where I'm going to do some practice problems for you guys. But it's actually quite simple. All you have to do these practice problems is to know these formulas. pH is equal to negative log of H plus POH is equal to negative log of OH minus. And then lastly, there's also the fact that pH plus POH is equal to 14. Anyways, I'll pause it here. Stay tuned for video part 2 so that you can see these practice problems if you need help with plugging in. So you got it.